The topic of my call today is about enabling 5G transport post-release 15 of 5G. You know, there's been a lot of talk in this conference about 5G as a topic. It's a very hot topic. Honestly, most of them were very focused either on the RAN or on the core, and they forgot that the mobile network has another portion, which is a transport. I know it's not as sexy as the RAN or the core, but it is still an important part. And if you want to enable 5G services end-to-end, and that's really the name of the game, then you need to take care of this. So we've been working about this for quite a while. But really, let's get started. And you know, 5G is about not just about the technology, but about new use case, new business case. I mean, if at the end of the day, 5 years from now, we'll sit in a conference like this and we all get into the conclusion that 5G was just another better RAN interface, then I think that we all as an industry have failed, because the target of this technology was way higher. And if you want to go to the original NGMN document or white paper that the operator community has published at the beginning of that journey, it has touched a lot of topics like massive IoT, like ultra-low latency, so new technologies, new capabilities, new use case, new business case. And of course, this brings to stricter requirements. It will result in a change of architecture and focus a lot on the end-to-end solution, because when you start to bring in latency as a parameter, when you start to bring in a new type of services, new business cases, you need to look at the picture end-to-end. Now, if I'm focusing on the transport domain, then you see a lot of new requirements, like a higher bandwidth, the support for low latency, the support for network slicing, and agility. So there are some good news here, okay? The good news is that 5G is the first actual technology that SDN and NFV were defined as a fundamental technology to support with it. And this is another a very important point to remind, because in this conference there were a lot of talks looking at virtualizing the core and stuff like that. That was a fundamental definition when the 5G journey started. So let's look at a traditional 4G architecture and see what was the evolution of this architecture towards 5G. So first, let's speak about the structure. In a traditional 4G network, we have the RAN, the transport, and the core. So the whole network is a tree structure going from the multiple RAN sites through the transport to 1, 2, 3, 4, like very few core sites. In the 5G, we are shifting that towards a few new concepts. First is a per service structure. So we can, in 5G, deploy multiple core instances to handle the core sites per need, and we can use a modular core. That fact is a result of the use of NFV technology, as well as the CAPS definition, the control plane, user plane separation. So you can see in 5G one slice that will have a core elements of a regular core, and another slice that is maybe serving a different use case, for example, a water utility that doesn't require the traditional components that you see in a traditional 4G network. For example, we don't need an MME in a water utility smart metering use case, right? I mean, the smart meters aren't going to move anywhere. They are fixed. So this is one change of architecture. A second change, which is, again, was highlighted throughout this conference, is the ability or the dynamic nature of the core. We will have user plane instances separated from the control plane, and they can move. They can go deeper into the network, running from the edge of the network, wherever the edge is. It can be a metro, even a central office. And last but not least, and this is a tremendous and very dramatical change, it will have a single orchestrated domain. So if you look at mobile network today, they are managed by a different department, usually in the operators, and to create a service end-to-end means that you have to break the request and send it to the different department, then assemble everything back. But in 5G, we'll have a single management and orchestration domain. And this is also what will enable us the end-to-end service nature for this technology. Now, looking at the mobile transport, so we can clearly see some trend. And again, for that end, and this is my personal observation, there is not a singularity point where we are either 5G enabled or not. I mean, yes, all the operators in the marketing material will say, okay, we've switched on our 5G network. That's great. Which 5G is it? Is it release 15? Is it release 16? Release 17? Each and every step of the way will have a different characteristic. And again, that was done with a close cooperation of the industry, all of the operators getting a lot of traction for the market for a much faster Ethernet. Then they decided to basically cut the 3GPP efforts into 2 steps or more than 2 steps and froze release 15. And this is, for that reason, today there are active 5G networks, and I'm seeing in the crowd many operators that are actually running these type of networks in production today. Now, in my talk, I will focus on release 16, and the reason for that is that I want to introduce you a new transport technology that we designed for the release 16 age, more specifically to hit several characteristics or use cases, the URLLC, or in other words, low latency use cases. There's the use of network slicing, which again, in release 15, is not well defined and is not present in all of the 5G networks that we see today. So my talk is focused there. There are tremendous work being done in release 15. Again, I'm not going to touch on it, but it's a very interesting topic. So what are the post-release 16 requirements and technology innovation? So the first topic is the topic of network slicing. And again, network slicing is a very interesting topic. I want to give you at least our observation or our definition for it, because you speak to 5 different people, you get 5 different opinions. If you speak in my country, which is Israel, you speak with 5 different people, you get 10 different opinions. So I want to tell you what we believe is a network slicing. So network slicing, of course, is the ability to curve a slice of the network and allocate it to a specific cause, whether the cause is a specific type of service or even a specific type of customer. Now, the second one is much more challenging. Why is it much more challenging? Because of the scale. Okay, so if we say at the beginning we'll have just 2 slices, one for URLLC, one for the rest, or even 3 slices, one for URLLC, the other one is for massive IoT, and the third one is for best effort. It's relatively easy, it's relatively doable. What if we want to say, okay, in our automotive slice, we want to have 1 slice for BMW, 1 slice for Ford, 1 slice for GM. That's a totally different type of story because of the scale of the network slicing. So we believe that network slicing, the end goal is that the network slicing will enable the operators to go to the second example and to serve or to offer network slicing as a business model, not just as a technology proposition to their different customers. So we'll need a fine-grained network slicing with hard isolation. And I will spend a second of what is the hard isolation, okay? So in the talk before me, the gentleman gave a very nice explanation about how he implemented a quality of service scheme in P4 switch. That, of course, will assure the bandwidth separation between the slices. And again, that can be used also in traditional slices. Quality of service is quite a mature and good technology. But what happens when you throw in latency into the game? What if in my transport network, I have to maintain a specific latency figure? Now, if I'm having 2 different slices, as one is overloaded, then the queues at the egress ports are becoming congested. Now, because we use the assured bandwidth, then we will not get packet drops, but the queues will get congested, so we cannot control the latency. And this is one example where a hard isolation must assure that all of the resources are completely separated, not just the bandwidth or the quality of service. And again, this is why we are targeting the hard isolation into release 16. This is where latency will get into the game, and this is where it's becoming very important. A second part is support hierarchical slicing. One of the use cases that is often mentioned is that one operator will slice or buy a slice from another operator, or even a customer that will buy a slice, but inside the slice, he will want to further slice it to the different services that he uses. Not every service will treat the same way. So a network slicing requirement will require to support an hierarchical slicing. And last but not least, we want to provide a per slice behavior. And this is, again, the difference between VPNs and network slicing in our definitions is that in network slicing, every slice will behave completely different. While the VPN just assures that there's no physical separation and the quality of service may be maintained, but the behavior of the network is uniform. In network slicing, I think we should take it a step forward and assure that the per slice behavior is mature. And again, per slice behavior is data plane, control plane, management plane. It's all the aspects of networking. Another very interesting use case is XOL. So we heard a lot about O-RAN, and O-RAN is about, okay, maybe we can deploy some sort of a cloud run or disaggregate part of the base station, running them somewhere else. But what is the interface? So by doing that, we created a new type of interface called Fronthaul. If you're looking at the different function split options, so some of them even contain a third segment which is called middle haul, but let's keep it aside. So we have a fronthaul and we have a backhaul, and the fronthaul requirements are much stiffer. But if we want to, and again, very much aligned with what we heard here in this conference quite a lot, if we want to create a situation where we can port the VNF from the local DC to the CO site to meet a specific latency requirement, we should be able to change the fronthaul and backhaul partitions, okay, in runtime. And the third and the second observation is that all of these should still coexist. Why? Because no 5G site will be a pure 5G site. Most of them, at least at the beginning, will co-locate in an existing cell sites, and therefore will still have to provide a backhaul 4G, traditional 4G, 3G backhaul from these sites onwards. So fronthaul will be just an addition to that. So we need to have a backhaul and fronthaul coexistence, and we need to have a multi-generation backhaul and fronthaul. So we are seeing that there are different transport requirements. We talked about the network slicing, hard isolation. We talked about the high network utilization and the ultra-low latency. Now, each and every one of them, and actually, even if you try a bit harder, you can probably come up with every two requirements. You can find a mature technology that exists today that can serve them very, very well. What is the challenge? This is the challenge. We need one technology that can serve all three of them together. And this is this observation led us to believe that there is a need for a new technology, not just improving on existing technology. So these are the kind of the requirements that we've listed: the hard isolation, the fine grind slice capacity, the per slice behavior. It should be a dynamic and flexible in a sense that again, some of the voices in the industry today, and I'm not arguing with them, are saying, this stuff is way too complex. Why should we introduce a new technology? Let's do a lambda separation, okay? Provide hard isolation? Yes, it does. It's a lambda. You cannot get any better than that. It's a pure optical layer 1. What about then IMC and flexibility? If I'm investing a whole lambda in a slice, how fine grained can I make it? How dynamic and flexible I can make it? Probably that would be a challenge. On the low latency, there's a distinction today. Again, I'm not going to go too deep into that, but there's a lot of distinction today between ultra-low latency, deterministic low latency, and ultra-reliable. So how can you assure that the reliability of the ultra-low latency service, and of course, Fronthaul. So now, why do we feel that URLLC require for a new technology? In an essence, there is a phenomenon in the network called microbursts. I'm not sure if you're familiar with that. It's usually something that happens when we go from a higher layer capacity to a lower layer. We still have the capacity. We are still transmitting a 5G from the core to the access, but because the interfaces closest to the core are much faster, then the bits are pushed faster to the interfaces, and the interface cannot transmit them. How do we solve it? By buffers. What buffer create? They create latency, they create jitter. So this is a big problem for ultra-low latency, and here there's a conflict, and that really was the fundamental idea that led us to believe that we need to have a new technology introduced in order to support ultra-low latency. So with that in mind, we've introduced X-Ethernet. X-Ethernet is our, I would say, internal name. I will touch about the standardization and the industry name later on. Basically what it is, it's a new next generation Ethernet technology. It's a layer 1.5 technology. It means that it's reside on the PCS layer. It's based on a technology that's coming from the data center world called Flex Ethernet, which is an interface technology. It's been standardized by the OIF. And we enhanced that, basically brought the concept of the switch inside to connect between the different interfaces, therefore turn it from an interface technology to a network-wide technology. It's another, one more thing that is very, very important to highlight. This is not a totally new data plane technology, but rather an enhancement to Ethernet. And we believe this technology will reside upon the Ethernet ecosystem to create a multi-folding plane elements, network elements in the future. So what does X-Ethernet provide us? It provides us per slice operational flexibility. I can choose which folding elements do I want to use. Do I want to use layer 1.5? Do I want to use layer 2, layer 3? Based on the service requirement rather than the network design. It's a new paradigm in networking, which is a bit maybe hard to grasp. It provides the hard isolation. Why does it provide the hard isolation? Because we're working on a layer 1.5 level. So when I allocate time slot for a slice, it's a complete and hard isolation. I cannot exceed that. I cannot change it. And all of the other physical resources reside upon it. So there will not be a mutual interference, and we did a very nice demo with one of our European operator demonstrating exactly that. The hard isolation and the hierarchical nature of it. So in X-Ethernet, what we can do is we can take a slice, let's look at the green slice, and then further slice it inside. So in this example, we've created a sub-slices based on the requirement and assigned them for each different service, and we can do that per slice. X-Ethernet is much more secure by design. Why? Because there's a very hard isolation. You cannot mirror, you cannot copy a packet because everything is happening in the bit block level, and there's a centralized controller that configures this type of service. So you cannot be, it's very hard to copy or to eavesdrop to an X-Ethernet flow. The hard utilization, the high network utilization, this is a very important game because for those of you who've been around quite a while, I'm usually being challenged at this point with saying, okay, so you just entered some sort of a TDM technology into Ethernet, so let's go, you know, TDM. What are you doing, guy? And this point was a very big challenge for us, but we managed to overcome it using the fact that the PCS layer really knows what it encodes and knows to identify an idle block, okay? And with XInternet, what we can do is we can schedule a best effort traffic on an idle block, therefore highly utilizing each and every slot, not just because we've did a hard isolation, we allocated the resource, so not just wasting that. Another very important point is the ultra-low latency support. Because we're doing a bit block switching and not switching and routing, we don't have packet buffering, no encapsulation table lookup, so we're getting a really nice figures around 200 nanosecond per network element when it will be ASIC'd. And last but not least, the ultra-reliable low latency. Again, in this, we need a new paradigm. The 50 millisecond switchover, which is very common in operator network today, simply won't cut it when you are targeting I would not say 1 millisecond end-to-end, but even 10 millisecond end-to-end across the entire network. You cannot work with 50 millisecond. So we have an opportunity, or we have a capability here to basically duplicate the flow, send it in an adjacent way, and choose on the receiving end which part of the which bit block to get. Because we are working on a PCS level, and you can see that in the industry itself, there's a convergence of 64-bit block format in the PCS layer, we can natively transport a lot of different protocols, like InfiniBand, Ethernet, and CPRI. Why do we highlight that? If you recall, we need the XSOL support, so we need to support both Fronthaul and Backhaul. With XInternet Flow, we can natively transport them to the end. So 2 more slides and I'm finished. Of course, this type of a technology is a tremendous change, and it needs to go into the standardization track. Apologize for all the open source guys. Yes, there's still standardization work in the world. And this work is ongoing in the ITUT. The next lecture is from China Mobile, which has been a tremendous partner in this. But there's a really big ecosystem, including test equipment vendor, chip vendors, equipment manufacturer, and operators that support this work. So it has gone through a long journey, and it's still ongoing. It's going through standardization in ITUT SG15. So to sum it up, and really apologize about the late, next generation mobile technology has new requirements and challenges. In 5G, the mobile backhaul and fronthaul will be an integral part of the mobile network, and we haven't spoke a word about the end-to-end nature of it and how does it work with the MANO system. There is a need for new data plane technology to provide the required capability to support ultra-low latency, hard isolation, network slicing, and of course the growth in the bandwidth. And this is one technology that we propose towards release 16. So I'm done.